So here's the dot structure for pyridine, and we'll start by looking at the carbons on pyridine. So pyridine has 5 carbons. Each of those carbons has a double bond to it, so each of those carbons is sp2 hybridized, meaning there's a free p orbital on each of those 5 carbons. I'm just going to sketch in those p orbitals on those 5 carbons like that. Let's analyze the nitrogen, and let's figure out the hybridization of this nitrogen atom. The best way to do it is to figure out the steric number of this nitrogen atom. And so the steric number is equal to the number of sigma bonds plus number of lone pairs of electrons. So watch an earlier video if you'd like to see how to do steric number in more detail. So we could say this is a sigma bond, we could say this is a sigma bond, and then we could say there's one pair of electrons on that nitrogen. So the steric number is equal to the number of sigma bonds, which is 2, plus number of lone pairs of electrons, which is 1. And so the steric number is equal to 3. So this nitrogen must have 3 hybrid orbitals, and therefore it's sp2 hybridized. So it has 3 sp2 hybridized orbitals, and therefore 1 p orbital. Right? So an unhybridized p orbital. So this nitrogen is also sp2 hybridized, and so we can go ahead and sketch in the p orbital like that. And if we look at the number of pi electrons in pyridine, right, there's 2, 4, and 6 pi electrons. So that fulfills Huckel's rule. So there are 6 pi electrons, and we can see that the pyridine molecule is a ring of continuously overlapping p orbitals. So these p orbitals can overlap side by side, and those 6 pi electrons can be delocalized throughout the ring. And so since this meets both of the criterion, pyridine is an aromatic molecule, so it has some extra stability associated with it. Now this lone pair of electrons on this nitrogen, that lone pair of electrons occupies an sp2 hybridized orbital. So we said that nitrogen contains, this nitrogen is sp2 hybridized, which means it has 3 sp2 hybrid orbitals. So one of those sp2 hybridized orbitals formed a bond with this carbon over here, one of them formed a bond with this carbon over here, and the last sp2 hybrid orbital actually contains that lone pair of electrons. So the lone pair of electrons on that nitrogen does not participate in resonance. That lone pair of electrons is localized to that nitrogen. And so anytime you see a situation like pyridine where you have a nitrogen with a lone pair of electrons and some electrons already participating in resonance, so those would be the electrons in magenta here. The electrons in magenta participate in resonance, so the electrons in blue cannot participate in resonance. They are localized to this nitrogen atom. Okay, so we've seen that pyridine is aromatic. Let's go ahead and do an example that's similar to pyridine. This is pyrimidine. All right, so let's see if we can analyze the pyrimidine molecule the same way that we analyze the pyridine. So once again, if I start with my carbons here, each of these carbons is connected to a double bond, so I have 4 carbons, and therefore each carbon is sp2 hybridized. I can go ahead and sketch in a p orbital on each of my sp2 hybridized carbons, like that. When I study the nitrogens in pyrimidine, I can see it's the exact same situation that we had in pyridine. Right? So I can see that there's a sigma bond here, a sigma bond here, and a lone pair of electrons here like that. And so I can see that this nitrogen is sp2 hybridized. And I can see that these pi electrons here are going to be participating in resonance. So for that nitrogen, it's sp2 hybridized. It has a free p orbital, so I can go ahead and draw in the p orbital there. And I know that the lone pair of electrons in blue, since this nitrogen is sp2 hybridized, that lone pair of electrons is going to occupy an sp2 hybridized orbital. It's the